In the last class, we discussed application of integrals. We began with lengths of plane curves. Uh, so just a quick review. Two key things in lengths of plane curves. And this is also called rectification. So these two equations, as we said, these are the most important. If we know this, after that we can solve any problem. This is in Cartesian form, this is in polar form. Okay. Next, so ds square, ds is the differential length of the curve. So ds square is equal to dx square plus dy square. And in polar form, it is ds square is equal to dr square plus r square d theta square. Okay. So that will be the length of the curve. When we integrate ds, we'll have to integrate ds either with respect to theta or with respect to r dr or with respect to r, uh, as the problem uh, defines, whichever is easy. That we'll see soon in some problem. As far as Cartesian coordinates are concerned, things are very simple. Either we have to integrate with respect to x or with respect to uh, y, and we'll get the lengths of the curves. So these are the lengths of the curves that we discussed last time. With respect to x, from x equal to a to x equal to b, the integral a to b under root 1 plus dy by dx whole square dx, and this is 1 plus dx by dy whole square under root dy if it is with respect to y. And in parametric representation, if x and y are represented by a common parameter t, x is a function of t, y is a function of t, then dx square, dx by dt the whole square plus dy by dt the whole square under root dt integral with respect to dt of this quantity from t equal to alpha to t equal to beta, that will give us the length of the arc. And in polar coordinates, when we do with respect to theta, it is r square plus dr by d theta whole square d theta. And when we do it with respect to r, okay, it is 1 plus r d theta by dr the whole square under root dr. So this was about the lengths of the curves. Now let's look at areas. So areas and the under curves. So let's begin. Area bounded by plane curves. I'm just again sharing the screen. So So look at this area bounded by plane curve. If y equal to fx, f of x is the curve, then I want to find the area bounded by the curve y equal to f of x, and between that and x-axis, in between the lines x equal to a and x equal to b. Now this is the area we want to find. To do this, what we do is take an elemental strip. Integral is addition of areas, right? Okay, so this is the elemental strip. Does not come perfectly, but okay. This is the elemental strip of width dx at a distance of x from the origin. So corresponding to x, we get the value y or f of x. Y is equal to f of x, right? So we get area under the curve y equal to f of x with x-axis from a to b is actually it is integral y dx. It is integral y dx from x equal to a to b, which is same as, because y is in terms of x, we write f of y as f of x, so f of x dx from a to b. Now look here, this is the elemental strip. It is a rectangular area, this one. Okay, very tiny strip. Actually, I'm showing it as a thick strip, but it's a tiny strip. This is a very infinitesimal length dx. So dx is the width, height is y. So y times dx is the area of this rectangle, this colored rectangle. All such rectangles added up from x equal to a to x equal to b. That gives us the area under the curve y equal to f of x from a to b. Now, suppose we want to find the area um, in terms of y. So let's look at that. Okay, I'll use this graph x, y, and we have a curve. Yeah, this is the curve. Now I want to find area bounded by the curve in between these two lines. The first case what was with respect to x-axis. This is with respect to y-axis. Y equal to c, y equal to d. Now, when I have to do this, I have to integrate with respect to y. Y changes from c to d. So how I choose the elemental strip? The elemental strip that I choose is this strip. So this is dy. This is okay. So this particular area, this coordinate is y, corresponding coordinate is x. So this length is x. So it is x dy. So integral x dy, y varying from c to d. This is equal to, I will write this function. It may be given in terms of y equal to f of x. I will convert it to this form. X is equal to g of y. I am finding it is not an inverse function. Instead of writing y in terms of x, I take the term x on one side and write x in terms of y. So I get integral x dy from y equal to c to y equal to d. That x is g of y. So g of y dy, integral c to d. Remember again, I am telling an important point that this g of y is not the inverse. Both of this x equal to g of y or y equal to f of x represent the same curve. Okay. Next. So this is area bounded with the x-axis, area bounded with the y-axis. So with area bounded by the y-axis, we'll get this entire area, this shaded portion. Now, suppose the function changes sign. If the function changes sign from, positive values to negative, then positive, then negative, then positive, then how to do this? When you find integral, this portion, upper portion, will have positive sign. I will mark this. I will mark this one. Yeah. This upper portion curve will have positive sign. F of x dx will have positive. This will have negative. This will have positive. This whole portion will have negative and again positive. So when we do integral, when we see this, an important point, integral a to b f of x dx is equal to integral a to c in this particular curve, a to c f of x dx plus integral c to d f of x dx plus integral d to e f of x dx plus integral e to f of x dx plus integral f to b f of x dx. Okay. Now this is positive value. This is negative because the portion of the curve is below the x-axis. Now this is positive. This is negative, and this is positive. Okay. Now, all right. So for finding integral value is algebraic sum. Of the above integrals. However, a big but, area, when we say area bounded by the curve with x-axis will be numeric sum. numerical sum okay, numerical sum of that means it is modulus. Okay, sum of the moduli actually, sum of the moduli of the above integrals. Why? Now, from integral point of view, positive, negative will be counted. From area point of view, this is a positive area. Now, this is an additional area. So this plus this we have to do for area. And then this is additional area. This is additional area. This is additional area. So we have to add up the areas. So we have to omit the negative sign. So for that, what do we have to do? We have to, so area under the curve, therefore, area bounded by y equal to f of x with the x-axis will be equal to, now, integral a to b f of x dx, it is already positive. Now, this c to d f of x dx is negative, so we have to take a modulus of it. Sorry, b to c. Sorry, this a to c and 1. This is a to c f of x dx and then c to d f of x dx modulus. Let's go up. D to e is positive, so maintain the positive sign. So even if you take modulus, it doesn't matter. Now e to f is negative. This portion integral is negative, but area we have to add up. Plus integral f to b f of x dx. Okay, this is a positive. So together we can straightforward simply write integral a to b modulus of f of x dx. This will take care of the entire thing. I take the modulus of the function. That means all negatives will turn positive, and after that I integrate. So directly it gets added. So area bounded is modulus of f of x integrated between a to b. So this is about area bounded. So again, I'm reviewing. The first part of the area was a simple curve y equal to f of x, which is having the same sign throughout. Its area bounded by that curve and the x-axis between the lines x equal to a and x equal to b. That was integral y dx. Now, area bounded by the curve with the y-axis from y equal to c to y equal to d is x dy or g of y dy from y equal to c to y equal to d. When curve changes sign, best is to just take the modulus of the function f of x integrated from whichever point to whichever point we require with respect to x. Now, next is area bounded by two curves. Okay. So this is talking about area bounded by two curves. So this is the figure. This is the figure. So first part is that the curve doesn't intersect. So let the curves y equal to f of x and y equal to g of x be represented by AB and CD respectively here. AB and CD, this is y equal to f of x, the first curve. The second curve is y equal to g of x. It is clearly shown. Now, assuming the two curves do not intersect, what will be the area? So the area bounded by the curve will be very, very simple. It's not. So area bounded by the curve. First, is the area bounded by the curve y equal to f of x from a to between a and b? We call this portion as the curvilinear trapezoid. Trapezium is like this. Curvilinear trapezoid means that this portion is a curve. So this term curvilinear trapezoid means this. So the shaded area is area of the curvilinear trapezoid APQB, this entire region, minus this unshaded region here, CPQD closed. So the first one will give integral f of x, integral a to b f of x dx. The second one will give minus integral a to b g of x dx. So together we can write this as upper curve minus lower curve dx. See this? This area is integral a to b y upper, the upper curve, minus y lower dx. Okay. So this is f of x minus g of x dx. Now let us say if the curve intersects in between these points x equal to a and x equal to b, how do we consider that one? So now, first of all, find which point it intersects. Okay. Now what we can do, very simple. Now, this is f of x, y equal to f of x, and this curve is y equal to g of x. Now, in this region, in this particular region, f of x is greater than g of x. And in this particular region, g of x is greater than f of x. So we split this to find this area bounded between the curves from A to C and C to B. So from A to C, upper curve minus lower curve. So f of x minus g of x, that is this one. And from C to B, it is g of x minus f of x, upper curve minus the lower curve. So it is g of x minus f of x dx. Together, if we have to integrate from A to B, we can write simply modulus of f of x minus g of x. This will take care of whether f of x is greater or g of x is greater. When we take modulus, it takes care of both. Okay, so we can find area by using this integral. Okay, so irrespective of whatever it is. So whether curve is intersecting or not intersecting, just take upper curve minus the lower curve. Now let's do in parametric form and in polar coordinates. How to do the integral? First, in parametric form, very simple. The parametric form, equation in parametric form, the area is given by, if we are integrating with respect to x, is integral y dx. All right. Now, y is a function of t and x is also a function of t. So dx will be dx by dt times dt, because x is a function of t. So dx basically is x dash t dt. So x dash is dx by dt times dt. So that's what we do. And t varies from t1 to t2. Now, if we are doing integral x dy, so dy will be written as dy by dt times dt integrated from t1 to t2. So very simple. No problem with this one. So if it's given in parametric form, it is easy. What if it is given in polar coordinates? So in polar coordinates, we do like this. Of course, in polar coordinates, there is no x and y. It is initial ray of the initial line, and this is the pole. Okay, this is the pole. Now, let us consider a curve. This is the curve. And the curve is given in terms of r as a function of theta, suppose. Now, I want to find out what is the area bounded by the curve in between, this is theta 1 and this is theta 2. Area bounded by the curve and the rays joining from the pole to the curve. So I want this particular area. To find that area, the simple thing that we do is take an elemental strip. We take a very small elemental strip. This angle here is d theta inside, and this angle here is theta. So this is at theta and this is d theta. Now the radius is r. R, it's a polar coordinate, so radius is r. So r d theta will give me this r d theta will be this elemental strip area. I'll plot it in green because it is in green. This is elemental strip. This is d theta. This is r. This is r d theta. And of course, either you take this as an isosceles triangle or you know the area of the sector. So dA is half r square d theta. Okay. So the total, so this is just this strip, this particular strip. All right. This is the expanded form of the strip. Yeah. So this dA is half r square d theta because area of the sector of the circle is half r square d theta. So this is dA. So what happens to the, how do we find the total area? Total area is integral dA, which is integral half r square d theta. From which point to which point? Theta 1 to theta 2. So that is how you get, or that's how we get this one. Area in polar coordinates is half integral r square d theta from theta 1 to theta 2. The other way, now if I want to integrate with respect to theta, of course we are integrating with respect to theta only. So this r is a function of uh, theta. So r is f of theta. So we substitute that r as f of theta. So you get f square theta d theta integral 0 to integral theta 1 to theta 2. So this is the concept of integrals. Okay, area under the curves. Okay, now let us start some problems. Problems on areas under curves. Areas under curves and rectification. So this part is very important for practice and simple problems, but uh, profound in terms of their concepts. Problems on rectification and plane areas. All right. So the first question, right? Find the length of the curve find the length of the curve y is equal to 2 upon 3 x to the power 3 by 2 between x equal to 0 and x equal to 1. This was an objective question in one of the GATE papers. Find the length of this curve. Curve is given and we have to find the length of the curve between x equal to 0 and x equal to 1. The solution, we have to find the length. Integral s, the length is integral of ds. Now ds we know is under root of dx square plus dy square. Now depending on where we have to integrate, we will pull out either dx or dy from this under root. తీసుకుంటున్నా answer. Don't. Okay. So s is integral ds. All right. Now ds is under root of dx square plus dy square. Okay. Now this integral. So because we are integrating with respect to x, we will integrate as integral under root of, take dx outside, 1 plus dy by dx the whole square times dx, x equal to 0 to x equal to 1. So now the question is, now we have to find dy by dx. Then we substitute, we get the result. So y is 2 upon 3 into x to the power 3 by 2. So this is given. Therefore, the derivative dy upon dx is 2 by 3 into 3 upon 2 x to the power 3 by 2 minus 1, which is, this is 2 by 3 into 3 by 2 is 1. So x to the power half. So derivative dy by dx is x to the power half. Now this is x to the power half the whole square. So ds is integral x equal to 0 to 1 under root 1 plus dy by dx the whole square to dx, which is integral 0 to 1 under root of, substitute this dy by dx as x to the power half whole square, that will give us x dx. Now this is a very straightforward integral. 1 plus x to the power half plus 1 upon half plus 1, integrated from 0 to 1. So we get 1 plus x to the power 3 by 2. So this is 2 by 3 into 1 plus x to the power 3 by 2 from 0 to 1. This is 2 upon 3. Substitute. We'll get 2 to the power 3 by 2 minus 1 to the power 3 by 2. So the answer was given in terms of a numerical value. So let us calculate that. So 2 to the power 3 by 2. That means 2 to the power 3 is 8. So under root 8. So square root of 8. So square root of 8 minus 1 is this, multiplied by 2 and divided by 3. So 1.2189. So this is 1.2189. This is the length, whatever the units are. So 1.22 units. So this was the answer. This was the option given in that gate paper. 1.22. Okay. All right. So this was a simple problem on length of the curve. Very simple one. Next, we'll go to a little difficult one. I hope you all have taken down this one. If you have to take down, you please let me know. Otherwise, you take down along with me. Keep hearing and taking it down along. Now, For the parabola, x square equal to 4y. Okay. Find first point, the length of the arc measured from the vertex to one extremity of the latus rectum. This is the first question. The second is find the area bounded between the latus rectum and the parabola. Okay. So let us start how to solve. First step is to draw the parabola. Unless we draw a figure, we'll not get a immediate idea, or at least if you're very good in figures on a mental calculation, you should be able to draw the figure. Now this is x is equal to x square is equal to 4y. So y is equal to x square upon 4. So of course I can use the grapher and do it, but purposely I'm doing. So now y is equal to x square upon 4. Y equal to x square we know. Y equal to x square upon 4 will be a parabola. This will be like this. Okay, it is symmetric about the y-axis because replace x by minus x, the equation of the curve does not change. So it's a curve symmetric about the y-axis. Secondly, it passes through the origin. And next, where is the latus rectum? We know the equation when x square is equal to 4ay and x square equal to 4ay, the focus of the parabola will be at 0 comma a. Okay, focus is at 0 comma a, and the ends of the latus rectum is a chord which is perpendicular to the axis of the parabola. This is the chord perpendicular to the axis of the parabola and passing through the focus 0 comma a. This is the focus. Now the ends of the latus rectum will be 2a comma a and minus 2a comma a from the basics of the equations of the parabola, what we have learned in our younger classes. So these are the ends 2a to a, 2a comma a and minus 2a comma a, and this is 0 comma a. This is now I need to find, the first question tells me I have to find the length from this point to this point, from O to, let's say, this end of the latus rectum is A, this end of the latus rectum is B. So either this length O to B or O to A. So I'll choose O to A because X will be positive. Okay. So what I have to do, see, y is x square upon 4. dy by dx is easy. Dy by dx is 2x upon 4, which is x upon 2. Now, length, the required length, this is the first part. The required length of the curve, the required length of the curve OA is, all right, we can represent this as S or L, SOA, is integral 0 to 2a, 0 to 2a, under root of 1 plus dy upon dx the whole square times dx. All right, 1 plus dy by dx the whole square under root times dx from x equal to 0 to x equal to 2a. So now let us do this. This is integral 0 to 2a under root of 1 plus x upon 2 the whole square dx, which is 1 upon root 2, take outside, integral 0 to 2a under root of x square plus 2 square. This is a standard integral which I had told you all to remember. The antiderivative for um, integral of under root x square plus a square dx is x upon 2 under root of x square plus a square. This we can get by integration by parts. Okay. Plus, the sign comes with the coefficient of a square. So if it's x square minus a square, it will be negative. Otherwise, it is positive. So plus a square upon 2 logarithm of log mod x plus root of x square plus a square plus c. Okay. So we have to use this. So I have been repeating when I was teaching integrals, I said these formula are very important. We will use this in application of integrals. So here we are. This is what we have to use here. Now, so let us use this. This is 1 upon root 2. So 1 upon under root 2. Now this is x by 2 under root of x square plus 2 square plus this is 2 square by 2. A square is 2 square. This is 2 square upon 2 log mod x plus root of x square plus 2 square, that is 4. Now this is the antiderivative. We apply the limits. So here, okay. Now our integral, okay. Here, what is the value of a? Y square is equal to 4ax. So a value is 1. So a in this curve, a value is 1. So that means we are integrating from 0 to 2. So a value is 1. So we are integrating from 0 to 2. Okay. So this is 1 upon root 2. Substitute 2 upon 2 by 2 square plus 2 square, plus this is 2 log mod 2 plus under root of 2 square plus 2 square. This is substituting the upper limit minus substituting the lower limit. When we substitute the lower limit, you get 0 plus 2 times log mod 0 plus under root of 0 plus 2 square. Okay. So this gives us 1 upon root 2 multiplied by, this is under root 8, this is 2 under root 2 plus twice of log modulus you can remove because it is all positive, 2 plus 2 root 2 minus twice of log mod root 2. So log root 2. So log A minus log B is log of A by B. That's what we need to do. Okay, or we can split this even further to simplify. Yeah. We can take 2 common. Or we can directly divide log of 2 plus 2 root 2 by root 2. This is easier. Then I multiply inside 2 plus root 2 log of root 2 plus 2. So this is the answer. So this is the arc length. So we see a simple curve, a very simple curve, but the arc length computation requires integrals. So this, yeah, correct. We can again take root 2 common and do it. It will be log 2 in the last term. Oh, correct. You're right. I'm sorry. It will not be log root 2. It will be log 2. Thank you. Thank you. So I will get, so if this is 2, then I'll get here 1 plus root 2. So this is the answer. Here it is 1 plus root 2. Okay. There is a division by root 2. Again, this is not root 2 doesn't come outside. This 2 comes outside. I made a mistake here. So this 2 comes outside. In that case, the answer will be root 2 plus log of 1 plus root 2. Yeah.
Sir, if we substitute 0 in the lower limit, the first term won't be 0, no, sir.
It will be 0.
Why? Root of 1 x square plus 2 square.
Multiplied by x is there, na?
Okay.
there's x that is there na, x by 2
Okay,
into
sir.
root of, so this x makes it 0.
Okay.
Okay, yeah, good. This was the length. So you see, it is a simple integral, but because you have this rational form, you have to use the antiderivative formula correctly and substitute the limits correctly and solve the problem. Okay, that is about length. How about the area? Area bounded by the lattice rectum and the parabola. This is the area. Any suggestions how to find this area?
Sir, finding the area about y and multiplied by 2
Area
from
about
0
y.
to a.
Okay, okay, good. You can find area about y. Integral. In that, one issue is that you will again have to, okay, you can do it. There's no problem because the function is simple. One method is you do integral 0 to a, that is 1. This is 2 comma 1. So 0 to 1, y equal to 0 to 1 integral x dy. So x you have to write in terms of y. So both ways we will do this. Okay, we'll do this problem two ways with respect to x and with respect to y. I'll show, and we need to uh, both ways we'll be able to do it. So this is the curve. Now this is the lattice rectum. This point is 2 comma 1. This is 0 comma 1. This is minus 2 comma 1. This is 0 comma 0. This is the origin. Okay. Now with respect to this shaded area is of course twice. Now area, shaded area, the required shaded area. I'll call it A. This will be equal to integral minus 2 to 2. I have upper curve minus lower curve. Y upper minus y lower. That means it is the area of this rectangle minus area bounded by the parabola with respect to the x-axis. So I get minus 2 to 2. Y upper is a constant 1. Minus y lower is x square equal to 4y. So y is x square upon 4. So minus x square upon 4 dx. Now because of symmetry, this is even. So it is twice of 0 to 2. 1 minus x square upon 4 dx. This will be twice of x minus x cube by 12 integral from 0 to 1, applying the limits. So when we apply the limits, now it will be 1 minus 1 upon 12 minus of 0. So we get 2 into this is 11 upon 12 If a equal to 1, you have to get 8 upon 3. Somewhere I've made a mistake. Y upper minus y lower from -2 to 2. Oh,
Sir,
this
upper
is
limit
0 to
will
2.
be 2.
0 to 2. I'm sorry. Upper limit, I made a mistake. So we get 2 minus 2 cube by 12 minus 0. Now this is 2 into 24 minus 8, that is 16 upon 12. So 2 into 16 upon 12, that is 4, 4 16, 4 3 is 12. So you get 8 upon 3 square units. So area is 8 upon 3 square units. Now alternative, with respect to y. Okay, integrating with respect to y. What we do from 0 to 1. So area is twice of, because this side is there, this side is there. You just choose this particular area. Multiply that with 2. So twice of integral x dy, y varying from 0 to 1. Now y square, sorry, x square is equal to 4y. So x will be 2 root y. 2 root y. X square equal to 4y. So x is equal to 2 root y, plus or minus, but we choose plus because we are choosing x as positive here. X is positive quantity in this particular quadrant. So we get 4 times. Now y to the power 3 by 2 upon 3 by 2 from 0 to 1. So a is 8 upon 3 times 1 minus 0. So same, we got by one integral. Here we have to do upper minus lower. So 8 by 3 square units. Here also 8 by 3 square units. Okay. So we can do it both ways. Okay, now I'll give you a problem for you to solve. So upper limit will be 2. Yeah, that for the previous you have said. I'll give you time for you to solve. Consider the curves C1, the curve 1, x square equal to 9y, and C2, y square is equal to 9x. All right. Find the length of the arc. Find the length of the arc cut off by one curve on the other. Second part is find the area bounded between the curves. Will you start? I'll give you time now. Please start. right, 5 minutes I've given to this problem. Length of the arc you'll have to do within 3 minutes. Anybody got? If you have got, just raise your hand. Do you need time? You can chat, or you can just say, do you need time, or should I? Should I continue? Yeah, someone has chatted. Unable to solve. Okay. All right. Just here. Area good. Area is right. Area is correct. What you have, one of you have said, area is right. Length, arc length. First thing to understand is these are two curves. We have to find their intersection points. So let's see the curve, how they look. I can easily draw using grapher, but in exam you will have to do it by yourself. Y square equal to 4x is this form. So this is y square is equal to 9x. This is the second curve, C2. Now x square equal to 9y will be this. All right. The same type of parabola, just rotated by 90 degrees. So this is x square is equal to 9y. Okay. Now they are intersecting. We have to find the points of intersection. One point is very obvious. This is origin. The second point, where will it be? Let us say this point is A. Okay. Now, what will be the coordinates of this point? So, point of intersection, because one very simple trick is because these two curves are symmetric. That means you replace x by y and y by x. You get this is symmetric about the line y equal to x. All right. In fact, if you observe very carefully, this is the shortcut for this problem. Observe this points of intersection will lie on y equal to x. So you take one curve and put y equal to x. So either, put y equal to x here, x square is equal to 9x. So either x equal to 0 or x is equal to 9. So you get 9, 9. That is where they intersect. Simple. So the curves intersect at the same points as they intersect with y equal to x. This is due to symmetry. This is due to symmetry about y equal to x. This is the easiest way to solve. So basically, y square is equal to 9x. substitute y equal to x. So you get x square is equal to 9x. So x into x minus 9 is 0. So x equal to 0 is 1 point, x equal to 9 is another point. When you substitute x equal to 9, then y square is 9 into 9, y is 9. So 9 comma 9 will be the point. This is the easiest. Otherwise, what we need to do is solve these two equations. Alternative is solving equation. Solve x square equal to 9y and y square is equal to 9x. This also we can do. Substitute from first equation, substitute y in the second. So we'll get x square by 9, the whole square equal to 9x. So x to the power 4 is equal to 9 cube times x. So bring it to this side, then x minus x cube minus 9 cube equal to 0. So you get x equal to 0 and x cube equal to 9. So that gives x equal to 3. Sorry, x cube equal to 9 cube. So that gives x equal to 9. So from this, either of this, you find the point of intersection. Now we want to find the arc length. So to find the arc length, either we use dy by dx or dx by dy. Which one will be simple? Better to use dy by dx. For which curve? Don't get into roots. So better is use the first curve, x square equal to 9y. So x square is equal to 9y, which implies dy upon dx is 2x upon 9. Therefore, arc length OA is integral x equal to 0 to 9, integral 1 plus dy upon dx the whole square dx. This gives integral 0 to 9 under root of 1 plus 4x square by 9 square, that is 81. Or I'll maintain 2 square x square by 9 square dx. Pull out 9 upon 2 upon 9 outside this bracket, outside the under root. So we get 9 upon 9 square upon 2 square plus x square dx. Now this is of the form integral a to 0 or a to b integral x square plus a square form. So x under root of x square plus a square plus a square upon 2. So this is a square upon 2 into logarithm of x plus root of x square plus a square. Integrating from 0 to 9. Two by 9 integral of, substitute, you get 9 under root of 9 square plus 9 square by 2 square plus 9 square by 2 cube. We'll simplify this. Logarithm of 9 plus under root of 9 square plus 9 square plus 2 square. Minus, substituting the lower limit, we'll get 0 minus 0 plus 9 square by 2 cube into log 0 plus under root of 0 plus 9 square by 2, you will get 9 upon 2. So let's do it further. So when we take 9 outside, okay, 2 by 9, I'll leave as it is. I take 9 outside, I get 9 square, because this 9 square I take outside the root, it will become 9. So 9 multiplied by 9 is 9 square. And this is 1 plus 1 upon 4. So 4 plus 1, 5, under root 5 by under root 4, which is 2, plus 9 square by 2 cube, same, exactly the same, logarithm of 9 plus 9 under root 5 by 2 minus 9 square by 2 cube log of 9 upon 2. Okay. So let's simplify now. Multiply by 2 by 9 inside. So we get 9 root 5 plus 1 9 cancels here, divided by 2 square 4 times log 9 plus 9 root 5 by 2 upon 9 by 2. So this we get as oh, I'm sorry, this is x by 2. So there is 1 by 2 term here. So yeah, 9 root 5 by 2 plus 9 by 4 times log of, multiply by 2 here and take 9 out. So we get 9 by 2 gets cancelled. You get 2 plus root 5. This is the length. This is the length. Of course, we can simplify this by, calculator you can use, and if so, this is the length. The second part is easy. This length of the curve was difficult because of the integral. The second part is area bounded by the curve. Area bounded between the curves. Symbol. That area is integral 0 to 9 y upper minus y lower dx. Okay. So y upper we get from this curve, y square equal to 9x, and y lower we get from this one, x square equal to 9y. So y square equal to 9x is the upper curve. So y will be y square equal to 9x. So y will be 3 under root 2 minus. Now x square equal to 9y. So minus x square upon 9. The lower curve will be this. So this is the integral dx. So now integrating 3x to the power 3 upon 2 by 3 upon 2 minus x cube by 3 into 9 0 to 9. So this is 3 cancels, 2 into, we get um, 9 to the power 3 by 2 minus 9 cube by 3 into 9 minus 0 minus 0. So this is 2 times square root of 9 is 3 raised to the power 3 is 27 minus this is 9 cancels, 9 square divided by 3. So 9 square divided by 3 will be 9 into 3, 27. So 2 into 27 minus 27 is 27 square units. So this is the area. Okay. So area bounded between curves is upper curve minus lower curve dx. We can do. So this is how we calculate area. This is how we calculate length. Tomorrow's class, I will discuss some very critical curves. That is some very important curves using polar coordinates. How the same problem we can do by Cartesian as well as polar coordinates. And in polar coordinates, the integral becomes very, very easy. So that's what we'll discuss in tomorrow's class. So we can stop now. Thank you. So please join at 4 p.m. tomorrow. Thank you.